Well, hello, and especially hello to the people that are in the band concert. Hope that you are having a productive rehearsal time. I'm excited about today and tomorrow because we are doing the heart of this class here, which is the fundamental theorem of calculus. And the fundamental theorem of calculus is something that you probably remember pretty well from last year. Our plan for today is that I am going to, first of all, just exhibit the theorem to remind you of what we're talking about. And then we're going to prove that theorem, building it up from the notion of average value. So, in terms of our plan, we're going to give the fundamental theorem in parts 1 and 2. And those two parts are complementary to one another. And then we're going to prove part 1 using a definition of average value. So that's our goal, and let's see if we can get there. All right, so the fundamental theorem of calculus ties together the notion of derivative and the notion of definite integral in this way. First of all, we take a look at the rate of change of what we might call area or accumulator functions. So, the notion of an area or accumulator function is that we're going to have some function f. Maybe this is my f right here. Now the variables get a little tricky for students, so I want to be clear about what's happening here. In this case, I have graphed f as a function of time t. So my axes are f of t vertically, and the horizontal axis is the t-axis. And now I'm going to start at an initial point, a, which is constant or fixed. And I'm going to now go out to a point x, which we can call our final point. And I'm going to add up or accumulate the net signed area here. Now the area word is obvious. The word to accumulate means to simply add up or find the total up. And so the idea is that I'm going to begin at A and I'm going to move out to X, and as I do so, I'm going to add on values of F as I go, so that I accumulate the total amount of F. Okay, what's that? Okay, yep. And so we can represent that accumulation process like this. So now what we're asking is, if x changes by a little bit, in other words, as I am in the process of going from x to x plus h, what is the rate of change of my accumulator function? And I think it's fairly clear to see that if I were to sketch a basic graph of my accumulator function, then the following properties would be evident. First of all, so notice that we have a change now in our axes. I am now using the integral from a to x of f of t dt as the vertical axis, and using the x variable as our x-axis. I think it's fairly clear that if I start at x equals a, then my accumulator function will be 0, because the integral from a to a of f of t must be 0. And then for this particular f, you can see that since f is positive, as I go out, I'm going to accumulate ever-increasing values so that my f will be increasing in some manner. And just from the graph of f, it looks like it's going to be increasing something like this. Okay. So the question is, if I were to draw myself a tangent line at this point right here, the slope of this tangent line is the derivative of the accumulator function. What is that derivative? And the answer is going to be this, that the derivative of the accumulator function at any point is simply the height of the curve. The rate at which I add on net signed area is simply equal to f of x. Now last year, you guys probably thought about this just in terms of formal substitution, because it's really easy to visualize the formal substitution. And you possibly thought, okay, derivative and integral cancel each other, or something like that, right? And that's not a wrong way to think, but that isn't the spirit of the underlying picture. So as we get into the proof, we're going to see exactly why this is so. So that's fundamental theorem part 1. FTC1, the rate of change of the accumulator function is the height of the curve. And this is what we aim to prove today. Justin, do you have a question? No. Okay. FTC2 is going to turn that around. And it's going to say, well, all right, how do I actually evaluate these accumulator functions? If, for example, I integrate from a to b some function f, what do I get? And the answer is, I get f of b minus f of a, where capital F is an antiderivative of little f. Yes, remember this.
Remember.
And this is extremely powerful and useful to us because at this moment, the only way that we have to evaluate definite integrals is to set up a Riemann sum and take a limit. And that's a very involved process. We don't like that. So we would love to be able to shorten that process with the fundamental theorem. Now, this is the traditional spelling of the fundamental theorem. However, for the purposes of solving differential equations and for a lot of other reasons, I almost always write my fundamental theorem like this. And if you take a moment and just do the substitution here, right here, you can see that I'm saying exactly the same thing. But I'm saying it with only one function involved. And I'm saying it in such a way that when we go to solving differential equations, it's a little more natural. So these two are equivalent spellings of the fundamental theorem part 2. We're going to prove fundamental theorem part 2 tomorrow. So that's our big picture. If you want a takeaway from today, this is it. How are we doing? Hopefully, really familiar from last year. We did this a whole lot. For whatever class you were in, did this a whole lot. You forgot it? Really? You forgot the fundamental theorem? The word fundamental is a tip-off that says, that screams, do not forget me. So there's a fundamental theorem of algebra. There's a fundamental theorem of number theory. There's a fundamental theorem of calculus. And those are all necessary. All right, well, let's now develop the proof of the FTC part 1. And we're going to develop that using the idea of average value So we're going to do a little sidebar. We're going to ask, if this is f of x on the interval a to b, and here I'm just using the axes f and x, then what is the average height of f? And I want to observe that this question right here makes sense because all of the different values for f of x that we have from really from f min to f max. So f min is down here, and f max is equal to f of b in this case, because f of b is the max. So, yes, sir? A is going to be a constant. If we have specialized accumulator-ish type functions, like if I integrate from x to x squared or something like that, we're going to come back and modify using chain rule. But for the canonical form of an accumulator, we're integrating from a constant fixed point out to a variable x. Okay, so the question about average height makes sense because we have a whole bunch of f values that range from f min to f max, and somewhere in the middle ought to be the average of all of those values. But the problem that I have is that f min and f max reside on a continuum if my function is a continuous function. And therefore, what does it even mean to find the average of a continuum of numbers? That's the problem that we have. And so we're going to answer that problem by appealing to a Riemann sum kind of idea. What we're going to do is to partition the interval a to b, like so. And for each subinterval, we're going to choose a c, and that c is going to be a sample point. So whereas in the construction of our Riemann sum, what we did was we took the c and multiplied it by delta x to get an area, here, instead of doing that, what we're going to do is to simply add up all of my f of c's as samples of my function. So just for the sake of it, in this example, I'm going to choose ci to be equal to xi. That is a right-hand kind of thing. Now, drawing rectangles, we're going to use the rectangles in just a minute. But the blue dots here refer to sample values of f. And how many of you had stat before? None of you. Okay. So does the idea of sampling make sense? So, for example, if we were to ask what is the average height of people in the school, then we could go through the entire population and add up all the heights and divide. But it might make more sense to pick a random sample. And we might do random samples from different grades or something like that in order to make it representative. Here, we're going to do a sampling of our function off of the partition. And we can choose the CI for our sample however we want. Okay. Then, we are going to divide by the number of sample points that we chose. And when we do, this is an estimate of the average value of f. So the key concept here is that I'm appealing to exactly the kind of I'm appealing to exactly the kind of averaging process that you are familiar with. We're adding up all the values and dividing by the number of those values.
Or the weighted one.
What's that?
The weighted one.
Well, we could do a weighted one, but here, and weighting is actually a huge concept in statistics. So you're right, but here our weight function is going to be just 1. Yeah. We're not going to do any fancy weighting with this. Okay? All right. Now, I look at this and I think to myself, this looks a whole lot like a Riemann sum. But what's missing here are delta x's to give me width. So what I'm going to do is to come back and insert those delta x's. I'm going to do it in this way. I'm going to come back and specify that my partition be an equally spaced partition. In other words, the standard delta x equals b minus a over n. Okay? Then, in order to insert the delta x's into this formula, I'm going to do a familiar trick. I'm going to multiply top and bottom by the same thing. So that f average is approximately equal to delta x times the sum FCI over n times delta x. Now, you can see the virtue of this because using my distributive property, since delta x is a constant value, I can distribute the delta x over my entire sum. And as an added bonus, since delta x is equal to b minus a over n delta x is therefore equal to b minus a. That's exactly it. So what we have now then is a legitimate Riemann sum. Okay. And now what I'm going to do in order to increase the accuracy of my sample size is to let the number of samples that I take go to infinity. And when I let the number of samples that I take go to infinity, my delta x shrinks to 0, and I'm sampling every single point on the continuum. Ta-da! I get a perfect average value. So that we say then, f average is the limit, as n goes to infinity, of the sum from I equals 1 to n of FCI delta x all over b minus a. And that limit is exactly the integral from a to b of f of x dx. So I'm going to give you a little bit of chance to catch up on the proof. The key points are, the key moves are choosing CI as a sample point and doing the standard averaging that you know about. Then pulling off my clever trick of multiplying by top and bottom by delta x. And recognizing that I've created for myself now a Riemann sum, which I can then make exactly precise with a limit. Yes, ma'am.
Did like the limit come from somewhere? Or did you
Right, I put it there specifically by taking the limit. What I do, notice I was very careful about the notation here. I said that the average value of f is approximately equal to my Riemann sum over n delta x. And by taking the limit, I then make this precise. So this is very closely allied to what we did all the way back back with derivatives, we said that the slope of the tangent line was approximately equal to the difference quotient, f of x minus f of c over x minus c. And then we took the amount of error away by appealing to the limit. And then we called that f prime of c. So the spirit of the calculus is essentially to create an approximation that can be made exact through the limiting process. And that's the entire big picture of calculus, both derivatives and integrals, and all of the various problems that we solve through calculus. Does that help? Yes?
So in the input theorem, all it is I'm using the real sum is the edit theorem.
So far, we don't actually know that it's an antiderivative. We're using this notation. It looks like an antiderivative notation. The name of that theorem is FTC part 2. Yep. So, as of this course, today, but not tomorrow, the only way that we have of evaluating this definite integral is setting up the Riemann sum and taking it away. Okay? Now, how does all this tie into FTC part 1? Well, first of all, we wonder, under what conditions can I find an average value? So we need a theorem. And our theorem is going to provide us with a guaranteed condition, but it is a weak condition. It is not as strong as it might be, because it's going to overlook certain types of functions. Our theorem is this, and this is called the average value theorem. If f of x is continuous, on a to b, then two things follow. The first is that the average value exists. Notice that I wrote the average value with division equals multiplication by the reciprocal. That's kind of the canonical form we'll see. The average value exists. This part I'm not really going to prove here. It depends upon the idea that you can integrate any continuous function. And that proof is beyond the scope of this course, but intuitively it makes a whole lot of sense that if my function is continuous, I should be able to bound its area with a max times a minus b and a min times a minus b. And since the area is bounded, then in the limiting case, intuitively it should be the case that it has a least upper bound, greatest lower bound, and those should be able to go to 0. That's the tricky part that I don't prove. I'm sorry, those should not be able to go to 0. Those should be able to approach each other. Their difference should go to 0. That's the part that I don't prove. And the second point is, there is a C somewhere in A to B such that f of c equals the average value. Now notice that the average value theorem sounds a whole lot like what other value theorem? The mean value theorem. And furthermore, you notice that the mean value theorem has a lot of similarities to my average value theorem as well. And that's not fully accidental. But the reason for the average value theorem is actually a little bit stronger than the reason for the mean value theorem. Notice I do not require differentiability. So the average value theorem is in some sense stronger because it requires less of a function. I don't need for f to be differentiable. All I need for it to be is continuous. And if it is continuous, I'm guaranteed that my f of c will hit the average value somewhere in there. let me draw a picture first and then I'll prove it. If this is my F, here's my A, and here's my B, then what I am doing effectively is I am saying that my function has to hit its average value somewhere in here. And actually, I drew that a little too high. I need to draw it a little bit lower, maybe right here. And the idea behind the average value is that it is going to split the curve into two different portions. And those two different portions are going to be such that the area underneath the average value is exactly equal to the area under the curve. In other words, any error that I have here will be compensated for by error here. So you can see I drew my average value a little bit too low in this case. I need to move it up so that the green here is matched by the green there. And we can see this simply by multiplying both sides by B minus A. On this side, what I have is literally height times width, which is the area of the red rectangle. And on this side, what I have is the net signed area under the curve. Okay? Now, the proof of this is delightfully simple. It depends upon the intermediate value. Since f is continuous, therefore, the integral from a to b of f of x dx is less than or equal to the max, f max, times b minus a, and it is greater than f min times b minus a. This was our min-max theorem, or our bounding theorem that we had. And if I simply divide both sides, then I get an additional bonus. And that is that I discovered something that was intuitively obvious, and that is that my average value is always between the max and the min. The average value must always be between the max and the min. So notice if I ask you where is the average value here, you can bound that guy by simply observing the max and the min values and saying it's somewhere in between. Okay? And because f is continuous, there is a c somewhere in a to b such that f of c is equal to this intermediate value that is between the max and the min. So I want to express the powerful idea that we have here, and that is that average value theorem is greater than, or is in some sense better than, the mean value theorem, in that it only requires continuity. And if I have continuity, I can average out my function, I can find its average value, and I can be guaranteed that the function will intersect its average value at least one point. And that's simply because of the intermediate value theorem. Physicists and engineers use the average value theorem all the time, because what they are often interested in doing is obliterating the details of a complicated function and simply saying, what's its average? When we average out a function, 1 over b minus a integral a to b of f of x dx, what we are doing is simply taking that entire function and pretending that it is constant on that interval. And that is the red line that I've drawn here, f average. So physicists will do this. They'll be presented with some kind of force like this, and they'll say, what's the average force over the time interval? Add up, divide by the width. So if you want a sort of mnemonic for average value, it is total area divided by width gives you average height. Think about that for a second. It makes a whole lot of sense, doesn't it? Total area divided by width gives you average height. Okay, now we've got a brand shiny new concept, the average value, and we've got a theorem that guarantees average values for any continuous function. Let us now go to the fundamental theorem of calculus part 1 and use that new tool. FTC. If f of x is continuous on the interval a to b, then, and actually to get my axes right, I'm going to need to use the variable t. So if f of t is continuous on the interval a to b, then the rate at which my accumulator function changes is the height of the curve. Picture first. And the picture is that I have a fixed point A, and I now have a point X that I'm moving out to. So, I want to compute the rate of change here. And the only way that I know how to compute derivatives for a new type of function is to use the limit definition. So I'm going to rewrite the derivative in terms of its limit definition, which is going to look a little bit different because my accumulator function evaluated at x plus h is this. This is the setup to make sure that this point is well understood by you. I sure can. Yes, sir. Oh, it's moving. X is changing. I'm doing a little arrow to show that X is changing. Like that. Yes, ma'am.
So, an accumulator function basically is like definite integral, but like.
It is a definite integral, yes.
It seems like the bounds are like perpendicular.
So in practice, the point A is fixed. Okay. So to make this definite, we might have something like the integral from 1 to x of t squared dt. And this would accumulate for us all of the net signed area from 1 out to x. And if x happens to be less than 1, then we would integrate backwards, and you would end up with the opposite of 7. The key point that I want to get a hold of is, does everybody see how this is the difference quotient up here? I'm evaluating my accumulator function at x plus h. I'm evaluating at x and subtracting. Does that make sense? Now, I'm going to pull off something clever using my properties of definite integrals. And that is that the integral from a to x plus h is the same as the integral from a to x plus the integral from x to x plus h. Let me move that down just a little bit so the previous line doesn't interfere. There we go. Okay. And all I did was to take this portion right here and split it using the additive interval property for definite integrals. And you can see exactly what happens. I'm going from a to x and from a to x plus h and subtracting. And when I do, all of this part right here cancels out, leaving me only with a little tiny thin sliver, which is the integral from x to x plus h. Interesting. Good. Yes. And yeah, that's right. It's going to be 0 as h goes to 0. So the form for my limit is 0 over 0. And that suggests that there's a common factor to be canceled, but I don't see it. Where is it? So now I'm going to appeal to my average value theorem, because at this continuous, it must hit its average value somewhere. And so I can rewrite this integral as the average height times the width, but the width is h.
Teachers, pardon the interruption, with the robotics class.
And so, you can see where this is going. I'm now going to take the limit as h goes to 0 of f average. But keep in mind that f average is between f max and f min on a given interval. And the interval that we're talking about is the interval from x to x plus h. So that as h goes to 0, f min and f max are the same value, which is f of x. Okay. Because of our shortened time period, I'm going to do one example on video, like 3 minutes.